Okay, so welcome to EN430, Environmental Process Technology. And my assumption, correct me if I'm wrong, by the time that you're entering this class, which is now, it means that you have cleared fluid dynamics, CE something, I've forgotten the code. The assumption also is that you have cleared environmental chemistry, including other chemistries such as CH110 and CH210. Okay, so that's basically going to be our working knowledge, our knowledge based on those courses. So basically, we're going to look at mass balance, followed by mass transfer, and chemical kinetics. So those are the three major topics that we're going to cover in this course. We're going to begin with mass balance, then we'll move to mass transfer. From mass transfer, we're going to go to chemical kinetics. And then the other smaller topics will fall in. Requirements for this course, in terms of assessments, we're going to have 3 assessments and 1 exam. The 2 assessments that we're going to have, the 3 assessments we're going to have a test, assignment 1 and assignment 2. We're going to have the test during residential. When is residential likely to be, according to your calendar? When is it slated for?
Around 24th May.
Which is very soon, huh?
Yes.
Okay. All right. So by that time, they understand. And 24th May, that's residential.
Yes.
For a period of how long?
It's normally about 5 weeks.
Wait, 5 weeks. Also 2 weeks learning and 3 weeks exams?
There's about 2 weeks learning, 1 week for CAs, then I think 2 weeks exams.
Oh, so basically 3 weeks, huh? Of learning.
Yes.
Okay, that's enough time for us to do the calculations, because we're going to do a lot of calculations that I feel that online may not be that effective. I think I prefer to do calculations one-on-one physically, so that at least when you're not clear, it's easy for me to just scribble something on the board, so that everyone gets it right there and then. Maybe I just need to improve my online tools so that I'm able to do that online also. But anyway, for now, I will dwell more on the theory online, then the calculations, we'll do them when we meet on campus. Okay, so that is just one moment. Okay, sorry about that. So 2 assignments that you're going to have to do. Now, how do we do the assignment? The assignments will involve calculations. Okay, we'll see how we do it. Otherwise, the assignments actually also involve calculations. So we'll see, and we'll work out something. But the intention was to have you do the 2 assignments before residential, so that you just do the test during residential. So we'll see how we work anyway towards that. Okay, so the notes that I shared with you are notes by Mr. Navuyanda. He was taking this course before I did, so I just basically got his notes. So I'm still working on my own notes. Okay, so maybe maybe just a brief intro. I'd like to know those who are working, where you're working, for me to just understand also maybe your level of understanding for this course. Master John, Mr. John, what industry?
Good evening, madam.
Good evening.
Yeah, so I'm the class lab for this program, and just an overview. Most of the
Mhm.
guys, I can say everybody here works.
Where is my interest?
Okay, so like for me, I work in the energy industry. I'm with the Energy Regulation Board.
Okay, all right. Energy. Okay, Madam Betha, which industry are you working? Or which sector?
Good evening, madam.
Good evening.
Yeah, I'm with water development
Okay,
and the Ministry of Water Development and Sanitation.
all right. Okay.
Yes.
And I don't know if this is Mr. Bubbly or Madam Bubbly. It just says Bubbly here. Okay, we'll skip Bubbly. Gershom, Mr. Yanika.
Good evening, madam.
Good evening.
Yes, madam. I'm with the Ministry of Health.
Okay. All right, Madam Maureen K.
Good evening, madam.
Good evening.
I work for Zambezi River Authority.
Okay. All right. Thank you. Madam Tabitha Mbewe.
Evening, madam.
Good evening.
I'm with Department of National Parks and Wildlife.
Okay. Thank you. And Mr. Zakaria, last but not the least.
Evening,
Good evening.
evening, madam. It's Tembo Zakaria from Kawambwa,
Okay.
Minister of Agriculture Engineer.
Agriculture engineer. Okay. Except for Bubbly, sorry, I don't know if this is a gentleman or a lady. I've not heard from. Or could it be someone using two devices?
No, she's actually a new student to us as well. We don't actually know her, so I just sent her the link. She requested it from the main group.
Okay. For whatever reason, she appears not to be answering, so I don't know if she's present or not. I'll conclude that she's not present because I cannot hear her. If she can hear us, maybe she can try texting in the chat box. Okay, so the reason of me asking is because we're going to look at processes in this course. So I just wanted to understand the industries where you're from, which are from you're basically from diverse industries or sectors. And nevertheless, I think the general understanding of environmental process technology should be far much easier for you than maybe for my full-time students who are just basically coming out of high school and now they're in class. So this should be much, much easier for you actually. So when it comes to environmental process technology and introduction, what are we looking at? So these are environmental technologies, okay, technological solutions of environmental problems, and they mitigate the impact of production on the environment. Environmental technologies are used in sectors such as industry, agriculture, services, and transport, and in everyday housework. So basically, environmental technologies are found just about anywhere. Okay, they're found in industry, in agriculture, services and transport, as well as everyday housework or everyday work around the house. And specifically, environmental process technology. This is a combination of environmental processes as well as process technology. So process technology is more on, especially I think for us in our country, we don't really have a degree in process technology. I doubt there is. But what we have done is that we have, since process technology is mostly aligned with chemical and environmental, so I think more of chemical engineers adopt more of the process technology than environmental engineers, looking at our curriculum. However, environmental process technology basically combines environmental processes as well as process technology. So we study a process Okay, and find optimum ways of running that process, as well as also now putting up those environmental processes, ensuring that these processes are not negatively affecting the environment. Okay, so which environmental processes are we talking about? Environmental processes include physical, chemical, microbial or macrobial reactions occurring at rates which are governed by kinetics and influenced by process conditions, including pH, temperature, mixing intensity, and so on. So natural systems, so there's environmental processes that happen in industry, and there are also environmental processes that happen in nature as well. So maybe examples of such processes that happen in nature under natural conditions such as lakes, rivers. Maybe we can have examples there. What natural processes happen in lakes that would co-environmental processes? You can simply just unmute and speak by a small group. There's no need to raise the hand on Zoom.
What's the question again?
The question is examples of natural systems or environmental processes that happen under natural conditions in lakes, for example, and rivers.
Erosion.
Pardon?
Erosion.
Erosion. Okay, what else?
Biodegradation of organic matter.
Yes, biodegradation of organic matter. That's an environmental process that happens. What other process can you think of? So you have photosynthesis happening, isn't it? You have respiration happening of aqua life. Those are also kind of environmental processes, isn't it? Because they also affect the environment, which in that case would be the lakes or the rivers, isn't it? The aqua system. So there are so many environmental processes that go on. Eutrophication also has to do with degradation. That is also an environmental process that would happen in a lake. So coming to industry now, which environmental processes, which examples can we give?
Copper extraction.
Mm-hmm.
Or I can just generally say mineral extraction.
Okay. Particularly what?
Come again?
Anything in particular?
The processes like leaching, smelting.
All right. So now, one thing worth noting also is that the systems, okay, they occur in some kind of container, isn't it? So when we looked at eutrophication, for example, and the photosynthesis of aquatic plants, everything is contained in a river, isn't it? That's where the system is happening. So wherever it's happening, wherever we have these reactions taking place, okay, the place where we have the main reactions taking place, we call that a reactor. So in nature, I'll repeat it could be lake, it could be a lake, a river, okay? And whilst in industry also, we could have those. We actually have those kind of reactors. So this could be a reactor for maybe examples. What examples would we give? Maybe in the food industry, trade kings, for example, when they are mixing their biscuits, when they put everything together, their flour, their milk, and everything is put in a reactor, isn't it? And then the contents are raised to a certain temperature. That would be an example. So another example that we're given here is, for example, constructed wetland systems, isn't it? So this one is an engineered system. While a natural wetland would just naturally happen, isn't it? It will be naturally occurring in nature. And also one could actually be engineered. Another example here is activated sludge. I hope we remember where activated sludge comes from. So this is a byproduct from the wastewater treatment plants. So that one also is like a mixture of the mixture. It's basically, sorry, I'm a bit distracted. I'm responding to Madam Bubbly. So please, I would appreciate your real name. I only have Bubbly for now. The name is gone. I think someone had mentioned it. I don't remember it. Anyway, come to process technology. Process technology includes analysis and modeling, as well as breaking down complex processes into elemental steps. So those in industry understand the importance of process technology, because it's from process technology that we're able to determine the optimum parameters, okay, for our processes. So what optimum parameters are we talking about? Examples are temperature, for example, temperature, pressure. Those optimum ones can be determined for us to ensure that we have as little waste as possible. So for us to maximize our materials, to maximize production, we need to operate at optimum operating conditions. So this process will involve an analysis. So analysis have to be done, modeling has to be done on different types of software, just to ensure, to help us. So modeling is done to just help us have a feel of what exactly is happening in our reactors and how these parameters are affecting the process at which point, okay, in time. So all that is factored in, and the modeling software is quite complex. But it makes life much, much easier compared to if we had to actually manually, or compared to how a few decades ago, before those automation of our industries or our processes or process technology, most of those calculations actually had to be done manually by engineers. But now you just have to enter your inputs and give your expected output probably, and then the software will run and give you which one would be the ideal temperature, for example, or pressure in which to run, or concentrations of your ingredients. Okay, so analysis and modeling, as well as breaking down complex processes into elemental steps. So this is to allow mathematical description and development of computer models. And these models are used to design and optimize reactors, control processes in reactors. Maybe an example from you, anyone with any knowledge of what kind of software is used in your current processes, if you know that, at your places of work. Anyone to share?
As for our industry, mostly in designing of structures, we use softwares like ArchiCAD, AutoCAD, Revit, and so on.
Okay. So for designing, isn't it? What about simulation? Modeling, would you know what you use? What kind of software you use currently?
Revit and ArchiCAD, they do model into 3D like designs, like you design a house plan, then it can show into 3D, and you'll be able to visualize how the design will come out after everything.
Yes, I understand. But simulations, I mean, like, there's kind of software where if you want to run a flow, for example, if you want to observe a flow and determine the parameters associated with that flow of water, for example. So it would basically run and you see the water flowing, okay, and it will tell you which one would be the optimum flow rate, for example, volumetric flow rate in that particular case. So it basically runs, it runs, how can I put it? It gives you a picture of how your process would happen. For example, if you're trying to make a drink, if it's in the food industry, to just basically, run everything and show you how the concentration would be at the end and any other parameter that you'd be interested in. Do you have those running where you work?
We don't normally use the software.
Yeah, otherwise
Yes.
I think they have to be used. I'm just not sure which department, depending on the organization as well. Otherwise, we should have some engineers, process engineers anyway, are the ones normally who deal with that kind of, those kind of simulations. Okay, all right, so we move forward. So those models, so those simulations, you run a simulation just to help you determine whether the diameter is the correct one, whether you need to reduce it in order to maybe get a desired flow rate, for example, or a desired type of flow. Okay, if you want something fast, maybe turbulent flow or laminar flow and so on. So those are there to just help you determine in your design also. So they can be used for design or just for like running the process to determine optimum parameters. Okay, so models are used to design and optimize. So these are, by the way, these are all exam questions. So a question has been, I'll share a past paper with you where you see these. And a question, I've seen this question before in papers. Environmental technologies are used in which sectors? So you have those answers. Environmental process technology is a combination of, in a short answer question. So you'll find that one also. Now, which other question have I seen here? This one also is an exam question. It will come every now and then. Which other one? This one also, the use of models to design and optimize reactors and to control processes in reactors. This one also. Okay, so to design and optimize reactors, to control processes in reactors also. So this would be so that's the use of models. So we use them to design and optimize reactors as well as to control processes in reactors. So when it comes to chemical reactions, these are distinguished from microbial growth processes. So we'll look at growth processes a bit later. Hopefully we'll have time for this, but now our main concern is the chemical reactions. So we can distinguish chemical reactions from the microbial ones in that for chemical reactions, only conditions such as pH, temperature, catalyst presence, concentrations are modeled for. Whereas in microbial or macrobial growth processes, characteristics of organisms need to be modeled for as well. Okay, so they're a bit complex. When you look at microbial, when you're looking at microbial processes, okay, your approach is different from when you're looking at chemical reactions. Chemical reactions are easier because you're only looking at the conditions such as pH and temperature and catalyst presence as well as concentrations. For microbial, they're a bit complex because you have to now look at the nature of the organisms that you are dealing with. Okay, another exam question is system analysis. What is system analysis based on? So on the analysis of a system. So this is based on 3 components. There's mass balance analysis, there's energy balance analysis, and there's momentum balance analysis. So the 2 are a bit beyond the scope of this course. What we are going to concentrate, you and me, is on actually mass balance analysis, which is the first thing that we're going to look at. Okay, so it says here also that this EPT, environmental process technology, so this EPT course addresses mass balance analysis only, which is a bit easier actually. Okay, so mass balance, what is mass balance? Mass balance analysis involves process analysis. So you're basically analyzing a process in a certain system, and the system means a volume with specific system boundaries. Examples of systems include a river, a flask in a laboratory, a pilot plant, and a groundwater catchment area. These could be systems. So they are what are known as open and closed systems. We'll see that there are some very good illustrations to help us understand what an open or a closed system is. So we have about an illustration for about 6 systems that we're going to dive into right now. So these are the systems. Okay, so there's system A. This is a closed system. Okay, so you can see that this bottle here is the system. Okay, so this bottle is closed. As you can see, it has a lid at the top, and that's the environment. So it's a closed system, however, it has energy exchange. So this is a closed system with energy exchange with the environment. Okay, the next one is, which is B. So this one has energy exchange with the environment and also within the system itself. Okay. So it has internal exchanges. System A has internal exchanges. So we come to system B. System B is also a closed system, as you can see. However, it has no internal exchanges. So this system A can be likened to a cold bottle of Coke, isn't it? You get a cold bottle of Coke, put it on the table. So what do you begin to see? There's going to be exchange of internal exchanges, isn't it, of gases from the Coke into that little air that is, you know, just before the lid. And also as that cold Coke is warming up, it's exchanging, there's some energy exchange happening between the environment and that bottle of Coke. That's maybe an example to give. For this one, it's something that's completely full. There's energy exchange happening with the environment. Okay, there's no internal energy exchange happening. With the third illustration here, we have an open system. As you can see, it has no lid. It has no lids, and there's an energy exchange. Can we please kindly mute our mics? There's energy exchange happening between the environment and the system. Well, while with the system D, it's a closed system. No exchange of energy with the environment and no internal exchanges within it. So these are the 4 types of systems that we're going to work with. Okay, so this means that there is no influence material pollutants into systems A, B, and D because they are closed systems, isn't it? There's nothing coming in. And there's no water, physical or chemical pollutants entering or leaving those systems. Only energy gets into and out of the system, while system C exchanges both energy and water with the environment. System C does not get influenced by either energy or matter from the environment. So these are also exam questions. Usually one of these will be picked and then you'll be asked to describe the type of system. Okay, so now we come to understanding the systems now in detail, defining a system and determining system boundaries. So for us to, whatever question we're given to do with mass balance, the first thing we need to do is to define our system and determine the system boundaries. The next step after that follows is analyzing what is entering, what is leaving, and what is being produced in the system. Okay, so mass balance relates 4 terms. So I'm assuming maybe mass balance may not be something that is completely new to you, but I'll still take it as something that is new to you, but I'm sure you have encountered it in other courses probably. So there's the term accumulation. Change in mass quantity per unit volume, kg per second. Then there's inputs, which is the mass inflow per unit time. Then there's output, which is mass outflow per unit time. And then there's production. This is mass production per unit time. Okay, so an example that I like to give in this particular scenario, by the way, will be, I think in about 6 minutes, our Zoom will be, the meeting will cut. I'm using a free version, so you just simply log on to the same link and we continue from there. So it has a 40-minute intervals. Unfortunately, I don't have a paid for one. Okay, so a good illustration that I like to use for this one is a pot of shima. Okay, a pot that you put on the stove to cook your shima, so that becomes our reactor. Okay, so let's discuss. Let's imagine our pot of shima there. And then you have, because before we come to accumulation, so you have your pots, okay, it's empty, isn't it? You place it on the stove. What is going to be your input? Let's quickly participate. At least we all cook shima or cook shima at some point, I hope.
Water.
Water.
You're going to add water, isn't it?
Yes.
Raise it to a certain temperature. And then what are you going to add?
Millimil.
Millimil, isn't it? And you're going to begin to stir. So what are your input materials for shima? Water and millimil, isn't it?
Yes.
Okay, so you're going to cook that shima. Assuming we all have.
What about the heat?
The heat is just to raise the temperature. So it's just for the parameters that we need in our reactor. So we're going to need a certain temperature, isn't it? That's the whole point of the heat. We need to cook at a certain temperature, isn't it? So T will be equal to a certain number there. What's the temperature we normally cook shima at? 120, 150. Okay, let's get 120 degrees Celsius. Okay, so now we've cooked our shima. So so how did we now, when we made we made the porridge, isn't it? And then it boiled for some time, and then we began to add millimil again, isn't it? That is still inputs. Then now after our food is done, what happens? When the shima is ready, where does it go?
We remove it and put on separate plates.
Okay, so, okay, let's put in one plate. So we'll put it in one plate, isn't it? You're cooking for yourself. So you put it on one plate. And then now, let's analyze now. Was there accumulation, for example? So accumulation from here says accumulation of substance A is input of substance A minus output of substance A plus production. So your input was water and millimil, isn't it? And your output now was what you're calling shima, right? Production of substance A. What is meant by production here is the understanding that in that reactor, in this case, we have the pot. Were there any reactions that were happening between the water and the millimil that caused more millimil to be produced, for example?
No.
Or more water to be produced? There wasn't, isn't it? So meaning our P will be equal to 0. Are we together?
Yes.
Quite all right, we added millimil again in the process, but that was also falling under input. Okay. So now, when it comes to mass balance, the understanding is that what K mean should be equal to what is leaving, provided there was nothing that was produced, okay? None of those substances, the input materials, none of them reacted such that more of that product was produced, for example. Or nothing was sucking up any of those inputs. So now I come back to the question. So the amount of water that you use, if it was 1 liter water, is the same that you have on your plate sitting, isn't it?
No.
So it's a difficult question. What happened to the water?
Some of it
Some of it evaporated.
Very insignificant amount, actually. Most of it actually remained in your, so we'll not count it because then the quantity is really low, that's evaporated, provided you're covering with a lid. So actually, it means that shima actually has water in it, isn't it?
Yes.
Yes.
People is like, it's okay. I know it's shocking, but actually there's a lot of water in shima. So your water, so you had 1 liter water, isn't it? Input. So output, you expect how many liters of water? Roughly 1, isn't it? Liter.
Yes.
Okay, let's say 995, which would be rounded to 1. Millimole, you had a certain grammage of millimole. Let's say maybe 500 grams of millimole input. So output, how much do you expect? Provided there were no losses in the pot, you expect 500, isn't it? Are you able to get me?